Here is a walkthrough of the linear expansion equation. This is a practice problem in 4.01. It says a steel beam is 5 meters long at a temperature of 20 degrees Celsius. On a hot day, the temperature rises to 40 degrees Celsius. What is the change in the beam's length due to the thermal expansion? So, of course, that key phrase there of thermal expansion tells us that we should be using the thermal expansion equation. It also goes on to say steel has a coefficient of linear expansion of 12e negative 6. So we have to watch out for those kind of numbers because they are written in scientific notation and often can cause a problem if you've forgotten how to computate that. So we'll go through each of those steps. The givens are nicely enough listed for us here on the side. So we know the original length, LO. We know the original temperature. We know the final temperature, and we know alpha, the coefficient of linear expansion. So with those, we can, I guess, do a little bit of side work to fill in all the variables that we will need. We should recognize by the wording here, what is the change in length of the beam? Means we're looking for delta L. Remember that delta, that triangle, stands for change. So we're not necessarily looking for the final length, which we could be asked to do, but in this case we're not. We're asked for the change. So we're really solving for that variable over here on the left side of the equation. So if I fill in some of what I already know, I'm looking for this delta L. It equals alpha, which is 12 times 10 to the negative 6. And I'll show you how to plug that in your calculator in a moment here. And we have to remember that negative, even though my computer's not letting me write it. There we go. And then LO is the original length, which we know is 5 meters. And then delta T, we have to think about what that delta T means. And again, going back to first semester, that triangle means change. So I really need to focus in on my TF and TO and kind of do a little side calculation here. They didn't tell me how much the temperature changed by, but very easily I can figure that out. So if I just go off to the side here to find delta T, the change of anything is always final minus initial. So I'm just going to take T final minus T initial. Or in this case, I've kind of run out of room. I'll write it down here. Delta T will be final 40 minus 20. Minus. So easily enough, I can do that in my head. I know the delta T is really 20, and that's something I should squeeze into my givens list then. Even though I calculated it, it's something I can use now. So that is 20. For some reason, the program doesn't want me to do an equal sign. We're going to get there. There we go. Okay, so easily enough, I'm going to put in a 20 here. So I really have everything I need now, and it should just be a matter of multiplying. But of course, the scientific notation does make it messy, so this is really a skill to continue to practice. We're going to, hopefully here, let's see if I can pull up the Google calculator. There it is. And I'm just simply going to type in what I had on that equation line in my substitutions. 12 exponent 6, actually I take that back. I need to put in the negative, negative 6 times 5 times 20. So really making sure this is typed in correctly to your calculator is going to be the important part. If you have a different calculator that's kind of your go-to calculator, whether it's handheld or on maybe another device, you really have to make sure you're comfortable with how scientific notation is entered into that kind of calculator. And if you're not sure, definitely reach out to your teacher and we can help you with that. So here we go. There's my equals, and I should get an answer of 0.0012. So I'm going to go back over to my paper here, 0.0012. There we go. And this is a change in length. So I really want to think about, well, what would that be measured in? Well, my lengths that were given, the LO, was in meters, so that should be no different. This should be in meters as well. And that would be my final answer. Now, this can also be written in scientific notation. So if by some chance this were maybe a multiple choice question instead, we could also express this by moving the decimal 1, 2, 3 places to the right. Or, actually, I didn't need the 0 there. It would be 1.2 times 10 to the -3. And that would still, of course, be in meters. So that's just kind of an extra to recognize that we can write this in scientific notation as well. But I think we're good enough here, since it isn't too extremely small of a number, to leave our answer in standard form. Hopefully this helps, and please reach out to your teacher if you do have additional questions.